I'm Michael. I work at Jane Street. Thank you for having me today. I'm going to tell you about a library called tracetypes, which allows for safe protocol updates via propositional logic. I think it has some pretty interesting ideas in it, so I'm definitely excited to tell you about it. So the problem this library is trying to solve is, given a collection of just executables which are out there in the world, they're in production already, for any given type, there's some directed graph about how these executables talk to each other. Furthermore, we're compiling some executable locally, and all these executables might be compiled from different versions of the code. All the ones in production, our local branch is probably ahead of the ones which are already deployed. And we want to know if doing deployment is correct. So we want to know if we were to place 6 executable like this one, are all the arrows, all the serializations that this executable participates in, is that still going to be valid? And as you might be familiar with, in order to solve this problem of being able to talk to old executables, typically, like, what you have to do if you want to change a type is you have to put in various tweaks to the serializer or the deserializer in order to maintain that compatibility. To get your intuition primed about the sorts of things that I'm talking about, I have a list here of common ways that people might tweak a deserializer or a serializer to be compatible with older executables. By far the most common is the first one, where you add a new record field but specify a default value, meaning that if that record field is not present, then that value will be taken. But there's other ones as well, and we'll discuss more of them later in the talk. So the solution that tracetypes proposes is to offer a language for writing serializers and deserializers which is expressive enough to, that it allows you to write all the version bridging sorts of code that we discussed in the last slide, but is also restricted enough that you can perform a static analysis on it, and you can actually verify that if you do a deployment that that deployment is going to be correct. The raw format that tracetypes uses for what's actually passed around between executables is something which is simple enough to, again, statically analyze, but also relatively expressive. It's either an atom, which is an unanalyzed string, or a dictionary, where you've got an A list of strings and nested raw.ts. For example, a natural encoding of a record here would be to store the the field names as the keys of the A list, and then the nested raw.ts would be like, so in this case, it's the variant stored as a singleton A list. In this case, it's a further record, which is, again, this record field is the key of the A list. The thing which makes this sort of a nice encoding is that all the deserializers and serializers that we want to express can actually be built up out of a couple of basic operations in a relatively straightforward way. For building up deserializers, the basic operations are taking a raw.t, assert its atom, assert it's an atom, and parse the string, or taking a raw.t, assert it's an A list, look up a particular key, and then recursively deal with the raw.t which you find there. We can display this in an actual OCaml interface. So this is wrapped up in what's called a decay deserializer.t. From such a thing, you can actually get out the function which takes a raw.t and parses it and returns a decay. These basic operations are the things I just described on the other slide. Atomic produces a function which asserts that the raw.t is an atom and parses the string with this function. Similarly, nested returns a decay t, where the raw.t is asserted to be an A list, and then the argument to nested is looked up in that A list, and the resulting raw.t is passed on to the other argument to nested. And then these basic ones can be combined using these sort of more generic combinator functions. For example, return will produce a function which ignores the raw.t and just gives back its argument. Map will just run its argument and then post-process by running this function on the decay that's returned. Both runs both of its arguments on the raw.t. Either it tries to run the first one, and if it succeeds, then it returns first of decay. If it doesn't, it runs the second one, and then returns second of decay. And then any takes in a list of decay t's and basically tries running them until it finds one that succeeds. For example, if you wanted to write a deserializer for a record type with the two fields here, so one way you could do it is you could say, okay, I need to get the foo field and I need to get the bar field. So let me look up the foo field and parse what I find there with int.upString. Let me look up the bar field and just take the string I get there. I need both of those things to succeed. And then I'm going to take the pair that I get by running both of those things and just put it into the record field, the record. So this can be done in kind of a natural way for records and for variants. As you might imagine, it's fairly cumbersome to write this sort of code by hand. So TraceTypes offers a PPX. This PPX just produces like the standard encoding of records and variants that you would normally do. So now what if you did want to use something non-standard? So you wanted to write some code to bridge between old and new versions. So let's take a look at an example where you have a record, but you want to use a default value for one of the fields. In this case, we'll say bar. So the way you would do this is you'd write a deserializer, which is very similar to the deserializer we had a couple slides ago. The only difference is in the deserializer for the bar field. Before, we just looked at the bar field and took whatever was there. Now we use the any combinator and first try that. So we do take what's there if it is there. But if there's nothing there, then we use return and just say, oh, okay, well, doesn't matter what's there, just take this default string. So this is also something that you, would want some PPX support for, and TraceTypes does provide it. You can see here that TraceTypes also offers annotations you can put at various points in the type, where you can say, okay, so you can generate the deserializer and serializer for this type, but at this particular point, use the generated value, but wrap it in any, and if it doesn't succeed, then use whatever's in here. Here's an example which this sort of thing is actually relatively common, although I didn't explicitly mention it before. But in this scenario, we have, the code starts with the type is something. It actually doesn't matter that it's a record field. It could be anything. The code starts in something, and then like later you say, oh, actually, there's more possibilities. And the code gets changed to the type that used to be the entire type is now some other type foo. And that's an argument to a constructor, and then there's more constructors. So basically what's happening here is you used to think everything that could happen was this, and you say, oh, wait, there's other things going on here. And so you stuff the old type into a constructor, and you add some new constructor of something else. It doesn't actually matter what it is for this example. I think this scenario is sometimes called retroactive unionization, although I don't need to call it that for this, but yeah, so now the problem is, suppose that we want to roll a deserializer. How can we write a deserializer for this type, which will also succeed on the old type? So the way that we do that is like this. So you have the old type, which is also part of the new type here. You have the new type here, and you want to write a deserializer, which will both work with the old and new types. So you write a deserializer which says, well, first try the deserializer just generated by the PPX, the standard one. So what's generated by this? And then if that doesn't work, well, try the deserializer generated by this, which was also the old type. And if that works, take the value you get and stuff it in the foo variant. There's also a serializer module, as well as a deserializer module. I actually won't say too much about it. It's almost exactly just dual to deserializer. So, for example, what you get out of it is a tick A to raw.t instead of a raw.t to tick A. This arrow is reversed. The map is called lift, and this arrow is reversed. You have an all function instead of an any function, and I'll leave it at that. So now let's think about the static validation part of this, namely given a serializer and deserializer pair, how do we know that the serialization is always going to succeed? So the idea is to think about what is present in a raw.t in terms of what paths are there. And so a path is basically a list of keys or a list of strings in terms of like nested lookups in the A lists, which are in the raw.t. And the way that we will check validity is we'll say, well, what is the serializer serializing? And is it enough for the deserializer to deserialize? In particular, we'll associate to every serializer a Boolean proposition S representing the paths that it's going to deserialize. And to each deserializer, we'll associate a Boolean proposition D representing the paths that it needs to be present. And we'll check that S implies D is a tautology. And in these Boolean propositions, the atoms are going to be these paths, these lists of strings. So, so they really do represent like what is actually present in the message which is being sent. It's actually relatively straightforward to see how the combinator portion of the deserializer and the serializer interface map onto operations on the propositional formulas, just due to their sort of abstract nature, I guess. So, for example, return is always true because it always succeeds. Map doesn't have anything to do with the structure, so it doesn't change the propositional structure at all. Both needs both of its arguments to succeed, so it's an and either and any both correspond to or because they only require one of their arguments. Well, either requires one of its arguments to succeed, and any requires just one element of the list that's its argument to succeed. On the other hand, both of the basic operations in the deserializer module, atomic and nested, don't affect the structure of the proposition at all. They affect the paths that are the atoms in the proposition. So, for example, atomic corresponds to the proposition, which is a single propositional variable, which is namely the empty path, the empty list. And nested, again, doesn't change the structure of the proposition. It just goes through all the atoms and prepends its argument. So it joins it to the path. So, for example, is the deserializer for this type compatible with the deserializer for this type? Well, no, and we can answer it using this propositional logic. So the proposition corresponding to this is just the foo, the path foo. And the proposition corresponding to this is the path foo and the path bar. So foo implies foo and bar is not a tautology. And so this is not compatible, and that's correct because this deserializer, of course, requires this field, which is not going to be serialized. On the other hand, what if we used the default value trick? So if we take still the deserializer, for which it says foo, but now we have a deserializer which has bar, but uses a default value of NA, is that going to be compatible? And the answer is yes, because recall the serializer here tries to look at bar, and if it fails, uses this, and this always succeeds, so the proposition is true. So we have foo implies foo and bar are true. Bar are true is the same thing as true. Foo and true is the same thing as foo. So this is foo implies foo, and so yes, it's a tautology. So now we can see a little bit more clearly how trace types tries to solve the problem which it's supposed to solve. Given a potential deployment where you say, can I take this executable and replace this one with it? Trace types finds the directed graph of how this type is being passed around. It finds all the arrows. It finds all the appropriate Boolean formulas from all these executables, including this one. And for each arrow, which this executable would be involved with, it forms the appropriate implications and checks if they're tautologies. As an implementation detail, it uses C3 stat solver, although that, of course, that's not fundamental. And yeah, that's it. That's the core of how the library works. Finally, to just say a few words about the actual production use. So we have used trace types in production for a little bit over a year and a half. It's used in a handful of projects. The one that I'm involved with uses it the most pervasively, and it's definitely been, I would say, a pretty big win. Like, it's enabled workflows that we haven't been able to do before, and it's eliminated, more or less eliminated a whole class of bugs. And it's been picked up by a handful of other projects, but within JStree as a whole, it's definitely still a niche library. I think partly it's because it's just a lot of new concepts for new users to pick up. And so we have some further steps that are aimed towards making it easier for new users to pick up. But on the whole, it's definitely something I'm quite excited about as a kind of robust solution to this problem. And that's it. Thank you very much.